All right, good morning, everybody. I hope you had a refreshing night and you had some time to think about all the stuff that we talked about yesterday. Are there any immediate questions that would be worthwhile to address? Actually, all the questions are worthwhile to address. Don't get me wrong there. Anything that burns on your mind? Nope. OK, so then let's get started with the program for today. Basically, what we have up is there's a few changes. Basically, we start out with the second part of the optimization presentation. Like yesterday, I think it's best if you ask questions while we're going. So I might digress, and there might be information out of order. But there is a few things that we need to touch on. So yesterday, we talked about launch configurations. And today, we have to talk more about memory optimizations and instruction throughput optimizations. So those are kind of the second part of the optimization talk. We're not going to do the streams presentation right at 11 o'clock. There's going to be half an hour on CUDA 6 at that point. CUDA 5 has been out now for about half a year. And we're right now in the process of releasing CUDA 6. So you probably should get access to CUDA 6 somewhere in January, February, early first quarter of 2014. So it might be interesting just to hear a bit of what's planned and what's coming out there. And then after that, we will just continue with the streams example and then see how it goes with lunch. But the idea then is in the afternoon, there's definitely going to be a session on Vampire, so on the performance analysis tool. But then the rest of the afternoon, I would say we just see what kind of problems that you have, or what kind of applications you're looking at, and what questions you have. So the idea is really that you can get started on your code while I'm around, while other people from CSCS are around that possibly can help you how to think about your problem and how to attack it. And then we can all go home and meet Sami Klaus and Schmutzli tonight. OK, optimization. So what we're looking at first is how to optimize the data motion between the global memory on the GPU and the GPU streaming processors, the SMs. So just as a refresher, how does the system setup look like? Right, you have on the host side, you have your basically your CPU and your RAM. There is caches in between and all that stuff, but there is a lot of electronics sitting between those guys, which is just the chipset on your motherboard that then talks across the PCI Express bus to our GPU. And the only places that you can directly put data into is global memory. There is some way of getting data into constant memory. It's a bit harder to get it into textures, but those are the only places that you can put data in from the host side. So everything on the device that needs to be computed has to come out of one of those three resources. And the question is now, how can we move data as efficiently as possible across this bridge? So if you remember the data that or the numbers that we attached to that yesterday, the bandwidth we have here is on the order of 10 gigabytes a second. The bandwidth here is probably about 180 gigabytes a second. Those are the numbers that we saw yesterday with the transpose example. Right? That was an example that moved data just from here into the streaming multiprocessors and then back out into global memory. Just an asterisk there. The numbers that are usually quoted for the GK110, or for the K20X devices, the one GPUs that you have installed in 30, the numbers there are usually 250 gigabytes a second for the bandwidth. This is with error correction turned off. Right? And so the number I quoted with roughly 180 gigabytes per second. That's with error correction turned on. So there's this fairly sizable penalty that you have to pay for the fact that you can detect bit flips, errors that, that might incur due to whatever reasons. So when thinking about optimizing the memory throughput, again, it's good to have pictures in mind. So basically, you have your global memory. And so this is the memory that sits on the GPU. And you have your streaming multiprocessors with your registers and the shared memory. And then you have this connection that has a certain bandwidth, right? That's the width here. And it takes a certain amount of time to access a data element from DRAM until this request has gone all the way to DRAM and comes back. So if you want to maximize the throughput, the amount of data that goes through this line, you need to make sure that you have, first of all, sufficient data that is being loaded per memory access, and that you have sufficient accesses that are outstanding in order to fill this entire area here. So it's the bandwidth times the access latency. So this is known as Little's law. And there's basically two ways of improving it, or of making sure that we're fully utilizing this area here. One is that we increase the amount of parallelism, that we have more threads that go out and request data, or we reduce the latency. Now that's a mechanical thing that we cannot really affect that. Similar to the bandwidth, it's a certain number of wires that there is available. So pretty much what we need to do is to make sure that we have a sufficient number of bytes in flight, or asking for a sufficient number of bytes, and make sure that we have every time that we can ask for bytes, we actually do that. Just as an illustration of what Little's law is, imagine you have an escalator, and it fits one person at a time. And every 2 seconds, you have one person arriving at the top, right? And now, it takes a certain amount of time until you get from the bottom to the top. In this case, whatever, 20 steps. So 40 seconds it takes until somebody comes from the bottom all the way to the top. Now, if you just have a single person in flight, you're being hit by the full latency, right? This guy starts at the bottom. It takes 40 seconds until he's at the top and is being spit out. Now, if you want to saturate the available bandwidth, which is the one person per step, you need to be sure that you have at least one person arriving every 2 seconds at the bottom that is then eventually being spit out at the top. And so you want to have, and so let's see, it's every 2 seconds that somebody gets out there. So you want to have 20 persons that are on the different steps in the escalator. And that's exactly the same that we need to make sure for this pipe between the DRAM and our streaming multiprocessors. We want to make sure that we always have sufficient requests for data in flight. So this is what you can observe here. It's probably a bit hard to read, but this basically shows how many memory requests we have active at any given time. And this is the percentage of the theoretical bandwidth that we achieve, and that's on a K20. And you see this is a typical flying curve where if you have insufficient number of outstanding requests, well, you're not seeing the effective bandwidth that is available due to the hardware. You're not being limited by the hardware, by the bandwidth of the hardware. This is only happening in this particular case at 160 lines. And I'm showing here what a line is. So on a single streaming multiprocessor, a line is 128 bytes. And so once you have like 100 times 128 or so, let's see, 100 is here, you're getting closer to the peak bandwidth that you can observe. The more, the better. So what we take from that is that you really need to make sure that they have sufficient load instructions that are going out there. And this can be, for instance, by making sure that you're loading all your data up front, then you do some massaging within your streaming multiprocessors, and then you're writing all the data at the end in a nice and coalesced fashion, and we're coming to that in a second. So this is another, could we shut the blinds here a bit? Is there a button? Child safety. Oh, okay, okay. So here's a slightly different way of looking at the same data. So remember yesterday we had this conversation about occupancy. So the number of warps that can be active on a streaming multiprocessor at any given time. And we said that on a K20, you have at most 64 warps that can be in any form of active state. So down here, we're listing between 0 and 64 warps active on a streaming multiprocessor. And it's 3 different curves for the width, for the number of bytes that are being loaded per warp. And so in one case, we're just loading individual words, individual floating point numbers per thread. So we have a single warp is 32 threads times 4 bytes. That gives you 128 bytes that are being loaded per warp. And that gives us one line. This is the blue line here. And you're seeing, once you're up at 64 warps per streaming multiprocessor, we're actually getting fairly close to the maximum, the theoretical bandwidth that we could achieve on this device. However, it really takes all 64 warps active in order to get to the full bandwidth that we possibly could achieve. Now, if we would be loading 8-byte words, so double precision floating point numbers, for instance, or long integers. At that point, each thread or each warp is loading 2 lines from memory, so 256 bytes. And at that point, you're seeing that you're actually getting closer to the peak bandwidth at a much smaller number of active warps. In this particular case, we're probably at about 40 warps per streaming multiprocessor. We're already hitting the maximum, the bandwidth that is that can be delivered by the hardware. And even if we go even larger, so 512 bytes per thread, at that point it only takes about 24 warps per streaming multiprocessor. So what do we learn from that? Well, again, we want to, for many applications, it's actually important that we get data as quickly as possible to the streaming multiprocessors. So we want to be as high up on the theoretical bandwidth as we want to use as much of the theoretical bandwidth as possible. However, due to other constraints, it might be that we cannot have 64 warps per streaming multiprocessor. Again, remember from yesterday, we might be using too much shared memory per thread block. So we cannot dispatch all 64 warps onto this streaming multiprocessor. Or a thread uses too many registers. Again, this would limit us in the number of warps that we have per SM. In those situations, we want to make sure that all the memory requests are actually wider, that we're not just asking for single floating point numbers per thread, but maybe 2 float numbers per thread, or even 4, if we want to get to the peak bandwidth. I see already at 9:15, lots of question marks. That's a bit scary. So, well, let's carry on for a bit, and then we see if it becomes a bit clearer later on. But I mean, the bottom line here is really that we want to make sure we want to be up here, and if you know from whatever, from your application, that you won't be able to run with more than, let's say, 32 warps per streaming multiprocessor, well, then you really want to make sure that you have at least 8-byte words that you're accessing per thread, rather than 4 bytes. Yes?
Maybe just what exactly do you mean by line? It's not cache line, right?
Well, it's, so as I mentioned yesterday, that the fundamental access that we have is at 32 bytes, 32 bytes per warp. So that's a quarter of a line. And so what the hardware can do is basically with one instruction, it goes out and fetches 4 segments. Now these segments can be contiguous in memory, they can be disjoint, doesn't really matter. But the hardware will schedule those 4 fetches roughly at the same time. And that then comes back, is being presented to the streaming multiprocessors like one line of data. So those are these 128 bytes that, so these 4 bytes or a single line. And yes, if we do have a cache hierarchy, and at one point, this is being reflected as a single cache line. So, but as you can see, I mean, it's actually not sufficient. If your occupancy is not 100%, then you want to have more than just a fetch for a single line in flight. You want to probably have, 2 or 4. If you happen, yeah, and well, I mean, you obviously don't want to load unnecessary data, right? So what this means is you have to rethink your algorithm in a way that you probably can fetch that much data. Let's see. For instance, if you want to do some finite difference scheme, right? We had yesterday already the thing about the finite differences, where we're loading data into shared memory, and then we're starting to subtract or add data from neighboring threads. But I mean, if you want to do this, you could, in theory, just load 32 floats, okay, at a time. Each thread pulling in 1 float. This would be one option. However, unless we have all 64 warps that are being running on the device, with this pattern, so something like A equals okay, we have our TID is something like this. Right? A pattern where we compute our thread index, and then we're just loading a single element, a float element out of this array. So this way, each warp, so the 32 adjacent threads, will fetch 1 float, and that is a good memory access pattern. We don't have any strides. We're not wasting any data in between. However, unless we have 64 warps running at the SM, with this pattern, we will not see 100% of our bandwidth. Right? Or to turn it around, if your kernel does nothing more than this, and you're observing now from measurements, right? You look at the amounts of bytes that need to be moved, and you look at the time that this kernel takes. From these measurements, you see that you're at whatever, 50% bandwidth. You're only getting 80 gigabytes a second. Well, you cannot expect more. This curve basically tells you that if you're running at 24 warps for whatever reasons, right? If you're just running at 24 warps, you cannot expect more than 80 gigabytes a second if your memory access pattern is just loading individual floats per thread. Now, if you would be loading something like this, so if your access pattern, and this is now whatever R, this is now a double array. If instead of loading per warp just 4 bytes, if you would be loading 8 bytes, and again, we're doing this all under the assumption that our occupancy is, let's say, 50%. Right? So 50% occupancy. That means we have 32 warps active. Okay? So this puts us at this point here in the middle. So with the access pattern that we're just getting a single float, with that one, and let me get the pointer here. With the single floating point number access pattern at 32 warps per SM, we can expect at most a 60% of the theoretical bandwidth. So instead of the 180 gigabytes, we get 60% of that, whatever, roughly 100 gigabytes a second. If we would be using doubles, so load twice as much data per thread, it would put us at 80% of the bandwidth. So, right, in those situations, it can be helpful to load data as double instead of loading it as individual floats. Now, again, it depends on your problem if this is even feasible. Right? You don't want to load unnecessary data. You don't want to right, just to artificially bloat your achieved memory bandwidth. But yeah, if we go back to the problem that I tried to get to, which is if we want to do finite differences. Oh, and I already started the chart up here. So, and eventually we need to load a certain chunk of data and then another chunk of data. Instead of having one load, do a lot of processing, and then do another load, we probably better load both chunks at once and then do the processing. So this should get us to a higher fraction of the achievable bandwidth than if we do it in individual steps.
My point was more or less, why don't they do this all the time? I mean, not the double thing. I mean,
Right.
if I have loads, I have loads, we probably have a reason for it. But this double loading, like these two.
Because, for instance, you just don't need that much data. Right? Imagine you want to do your kernel should do, actually that's a problem I really had. Your kernel should do matrix-matrix products. And your matrices are only 5 by 5 elements. Okay? So you have, for that, you need 3 times, right, you have A times B goes into C. Okay? So you need 3 matrices that are being loaded. But that's 3 matrices being loaded 5 by 5. So that's 25 elements per matrix. Times 3, it's 75 words or 75 floats that we need in our problem. So in this case, it probably wouldn't even make any sense to load these two, to load it as double, simply because we don't have that much data that we need to operate on. Right? So you don't want to waste to load data that you are not going to use. I mean that is that's one of the one of the starting premises. But then if you need to load a large chunk of data per thread block, sorry, if you need to load a large chunk of data per thread block, then you might be better off to load it as larger chunks per thread rather than having multiple loads per in sequence. And keep in mind, this is only relevant if we're running at lower than maximum occupancy. Right? If you run at full occupancy, if you have 32 warps in flight on the SM, at that point it doesn't matter whether you're loading now your data in 4 words, 4-byte words, in 8-byte words, or in 16. It doesn't matter. In all cases, you're getting to the maximum achievable bandwidth. So it's really just a question when you're operating in this regime, right, where for whatever reasons you're limited by the number of threads that can be executed on a, the number of warps that can be executed on the SM. Is that roughly understandable? Okay. And now you probably want to, so here is just a laundry list of different things that you can try in order to make sure that you're actually getting all the way to the maximum number of concurrent memory accesses. Right? The one is that you just want to make sure that your sizing of your thread blocks reflects the access pattern, that you have as many threads available as possible that could possibly load data. Now, if for instance, if your occupancy is limited by the number of registers that you have that you're using per thread, there is actually compiler flags that allows you to limit the number of registers used per thread. So it's the minus max R reg count. These options are just band-aids. I have yet to see a case where it really helps to use that option. But it's good to know that this might be around as a possibility. And so this is kind of we're trying to increase the number of warps that can run concurrently. If you remember the chart that I had before, we're trying to get onto the right-hand side of that chart, where it doesn't matter whether we are accessing data in 4-byte chunks or in 8-byte chunks. That would be one possibility. So getting us more to the right-hand side, or alternatively, getting us to one of the curves that is higher up. So trying to load 4, 8, or 16 bytes per thread at a time. Again, that might be possible or may not be possible. Yes? Yeah? Right. No, so in this case, A and B will end up in registers. So how many of those pages can I use? OK, if you have a signal kernel, whatever. And let's do here another. So we have a kernel that takes an integer array and a number, and we do the usual thing. So we have the thread ID is whatever, block dim dot x times block ID x dot x plus the thread ID x dot x. Okay, this gives us our linear array of the current thread. And we do A is whatever we had. Oh. our array of TID. And we do some processing, and at the end, we do an array of TID is result. And on the way here, we do as my result is some kind of function of A. Okay. So in a case like this, you're most likely just ending up with using registers. So what happens in the process of translating this kernel, it goes into this intermediate assembly language, this PTX. PTX has an infinite register file. You have as many registers as you want. And then when you're generating the actual instructions for the device generation that we have at hand, at that point, you have algorithms that say that do the true register allocation. Now, it tries to keep the register footprint as small as possible. And again, as long as you're below 32 registers per thread, there's no danger that you might limit your occupancy. So up to 32 registers, the compiler is fairly generous and just hands it out. Once, depending on obviously how much state that you need to carry around here in between, it can become a problem. And so the compiler then tries to rearrange your code to limit the amount of registers that you're using. But in some cases, it might not be possible to do that. At that case, it will do the so-called spilling and automatically convert, let's say, this variable A into a local variable. So a local variable is one that sits in global memory, but you have an individual version of that variable per thread. Okay? So this is when the compiler then says, oh, I just don't have sufficient registers for all that. I need to push it out into local memory. So that can happen when you just have a very large kernel. That's, by the way, one of the reasons why you probably want to keep your kernel size relatively small. That's a very fuzzy number or a fuzzy concept. But you don't want to take an entire application and just stuff it into a kernel. That most likely will just blow your register consumption, and therefore you're not getting a good performance. Because every time now you're accessing this variable A, it actually has to go out and fetch it from global memory and pull it back into your registers. So spilling is nice. In some cases, it actually doesn't hurt you that badly. But you want to be able to avoid it as much as possible. And that, by the way, here you see this max R rec count. Right? Actually, let's step back in one second. So in the best case, you're using less than 32 registers per thread. And there, it has no impact on the occupancy, right? We said the register file of a Kepler GPU is large enough to hold 32 register per thread and have still 64 warps. Yes?
So even if your occupancy is lower, some other reason, what happens?
No, so I was just getting there. It's like, right, so ideally you have 64 warps in flight. Now if your kernel is complex, the register allocator will just start using more and more registers. So for whatever reason, now you have this amount of data. You need 48 registers. Okay? What that means is that now you suddenly can no longer have 64 warps on this SM at any given time, because you cannot fit 64 times 48 registers times 32 threads per warp into our register file. We just don't have that many registers. So what it will result in is that fewer warps will be dispatched onto that streaming multiprocessor, which is equivalent to you're reducing the occupancy on that SM. And as you now have a lower occupancy, well, this would also allow you, for instance, to use more shared memory because per thread block, because you're already limiting your occupancy. I'll draw some more pictures on the occupancy. I see that this is probably a concept that we need to touch on. But to come back to this one, right? So if you have a complex kernel, the compiler by itself will just start raising the number of registers that it uses. However, we have now a limit of something like 256 registers per thread at most that can be used. But this could impact your performance. So you can use this flag max rec count, or on a kernel basis, you can use launch counts that tell the compiler not to use more than a predefined number of registers. For instance, you could say max rec count equals 32. This will tell the compiler, don't use ever more than 32 registers per thread. But given that the complexity of your code is already so big that you would need more than 32 registers, what it will then do is it will spill them into local memory. Yes? Is there an equivalent for OpenACC? Directly as part of OpenACC, I don't think so. The OpenACC compilers allow you often to control that. So I'm fairly positive that on for the PGI compiler, you actually have the equivalent of max rec count. The problem about max rec count is that it's a global sledgehammer, right? If you have a large application that has many kernels in the same file, well, you're applying this to all the kernels that sit in the same file, which, yeah, could be too limiting. Okay, let's draw another picture for the occupancy. So imagine we have this concept that on a streaming multiprocessor, we have these 64 warp slots. So at any given time, the scheduler can pick one of these 64 warps to issue the next instruction from. In the simplest case, all of those are full. Our configuration is such a way that we have a warp ready that's available for execution. In order to get there, we need to make sure that our thread blocks have the right configuration. So we have, in addition to these 64 warps, we have another table, which are the active blocks. The active thread blocks. So imagine a thread block that's we have shared memory per thread block. So there's some accounting that needs to go on to figure out like which warps belong to this thread block and so on. So that's why we have another static resource that keeps track of the active thread blocks. This goes from 0 to 15. So we have 16, a maximum of 16 thread blocks that can execute on a given device. Then we have another resource. This is the register file. This is just a huge file of registers. I would need to do the math again, but it's 32 times 32 times 64. So that's 64K of registers. And it's not K bytes, but it's K registers. 64,000 registers. And then we have shared memory. This is, in the simplest case, 48 kilobytes. Okay. So now let's assume we have a kernel. A kernel that uses whatever, 29 registers. It uses 0 bytes shared memory. And we have a large enough, and we have 128 threads per thread block. Okay, that's something you can control. Those are all parameters you can control from your kernel. For instance, like the one we had yesterday for the transpose, probably falls into this category. So what does that mean? With 128 threads per thread block, 128 threads, that's 4 warps. So we use 4 warps, and we have, per thread block, we're using 4 times 29 registers, which is 126. So 126 registers. We're still not using any shared memory at all. OK, and we have the 4 warps per thread block. So assuming that we have a sufficient number of blocks that we want to process, the scheduler on the device sees that we can put, well, 4 warps, so that's 0 to 3 per thread block, and it can do that all the way up to 63. So that's 16 times the 4 warps. That means we're filling all the slots for our active thread blocks. That's fine. We're not being limited by that. We're not being limited by the register file because we're using less than 32 threads per warp. And we're not using any shared memory at all. So the fact that we have these different resources that have fixed hardware limits is not limiting us in the number of available warps that we had at any given time that we could select from. Now let's look into the other extreme case. Let's assume we have we're using 256. So that's the green case. Let's look at the red case with 256 registers. And we're using 16 kilobytes of SMEM per thread block. And we're using just 32 threads per thread block. Okay. So where to start? 60. So the amount of shared memory that's being used, that's something that the scheduler sees when the kernel gets launched. It sees we need 16K. So at most, we can put 3 thread blocks onto this streaming multiprocessor, right? Because we just don't have sufficient shared memory to accommodate everybody else or more thread blocks. So at most, we're going to have those 3 active blocks. And they're filling all of shared memory. Now, given that we use 256 registers per thread, now we need to do the math. But what is 256? 256 times the 32 threads that we have in a thread block. What is this? This is 16 times 32 times 32. That's century. So that's 16 kilo registers that we need. We need 16 kilo registers per thread block. 3 times 16 kilo registers, that's 48 kilo registers. So the size of the register file is not a limiter. Right, so we're limited to 3 thread blocks already due to shared memory consumption. But the amount of registers still fits into the, that we need for these 3 thread blocks is still sufficiently small. So that's good. Register file size is not a problem. Yes? No, it could be more. It could, right, but that's getting fairly tricky to actually get the scheduler to pick those, to make sure that you have more of the different types of kernels executing at a time. So yes, it just makes the story even more complicated if you're adding into the mix the fact that you might have warps from different kernels mixing in. But so in the simpler case, right? Actually, that's a feature has not been around for a very long time, that you can even have multiple that you can have threads from different kernels sharing the same SM. So it's easier if you just think in terms of having a single kernel that needs to fill at least one SM. And then, right. So we said the amount of register we're using is not limiting us, but we're limited by the amount of shared memory. We can have at most 3 active blocks. Now, given that each thread block only has 32 threads, we're only using 3 of the 63 available warps, right? We have 32 threads per thread block, so a single warp per thread block. We have 3 thread blocks. That makes the total number of warps that we have at any given time up for execution just 3. So we're very likely going to hit the situation where these 3 have issued, for instance, a global memory load. And they have to wait until this load is being satisfied, until the request has been satisfied. There's all these empty slots where the device most likely could do something, but we have no work. Right? Because all the only 3 warps that we have running at this given time, they're waiting for some other resource. Okay, so this is where, and then just as an exercise, that the occupancy in this particular case is going to be 3/64, which is a fairly low number. Right? That's in the, what is that? A few percent. Something like that.
Your graph was
yeah, I mean, if this is a pathological case, you definitely don't want to be in this situation. You mean this graph here? Yeah. Yeah, I mean, as you can see, right, there's just no way of getting anywhere near a decent bandwidth if you're at that small occupancy. Yes?
these figures and graphs and calculations, what you draw here, is just what this Excel sheet does.
Exactly, exactly. I mean, it is, as you can see, it's kind of, it has all these different constraints that you have to satisfy. And that's exactly what the Excel sheet is about, right? You're plugging in, I mean, like we did here, you're plugging in the number of registers you're using, you're plugging in the amount of shared memory you're using, and you're plugging in the number of threads per thread block. And the sheet will tell you which one of these resources is going to be the limiter. See? And it also gives you some idea of what if I would change my shared memory footprint? What if I would change my register footprint? Because in some cases, you see that your kernel uses 33 registers. Okay? Well, at that point, it might be tempting to look if there's a way of just rearranging the code in a way that you're reducing this memory, the amount of registers that is necessary. Mm-hmm.
The number of registers, we just estimated by the number of local variables?
No, it's very hard to just stare at code and try to figure out how many registers you're using. The way you would want to do is this is by, and we should do that as an exercise, but basically it's NVCC. This is too aggressive, this red. Minus X PTXAS dash options minus V, and then it might be about, you would need to look up the demand page again for, or the help for NVCC. It might be without the X, so it's. We have the problem that many of the options are actually at least 2 variants that you can use them. And so it might be that it's just PTX AS options. So I would need to look this up. But it's a quick find there. So what this will do is that when NVCC actually generates the binaries for your architecture, it will tell you how much memory you used and how many registers it needed. So yeah, if you still have the transpose example yesterday, you can just easily modify the make file and add this option, and then you will see how many registers that you're using. But yeah, so this is kind of in hindsight. Then you know how many registers you're using. Then from that information, trying to figure out how to change the code in a way that you're reducing this consumption, that can be a bit hairier. I'm trying to think if this tool becomes public or not, but there is a tool that actually allows you to see, as a function of instructions, how many registers are being allocated and the lifetime of each one of the registers, because that can oftentimes help you to find something, to find a bottleneck. I mean, it's oftentimes not what you think would limit the number of registers. What happens, for instance, is that if you have a somewhat complicated index calculation, and you're using this early on in the code and later on in the code as well, again, a typical memory access pattern where you're loading something due to this complicated expression, and finally you're storing it, again, due to this complicated expression, there is a certain likelihood that this complex evaluation will end up in shared memory, in registers. And it will be keeping these registers occupied for the entire lifetime of the kernel. And so, yeah, it could be useful to just do a recalculation of that expression later on. You can look into things like if you have modulo divisions, or you need to compute the remainder. Those are cases that often use quite a large number of registers. That all then depends on the particular version of the compiler that you're using. It's unfortunately at that point a bit guesswork, trial and error, figuring out if you can reduce the footprint. The important part is that you know whether it's possibly worthwhile to do it or not. And this is where the occupancy calculator comes into place. And right, as I said, if you're seeing that you're using 32 registers, and you're seeing that you're limited by the achievable memory bandwidth, at that point it might be worthwhile to invest a little bit of time to try to get your register count down, just to increase the occupancy. But don't get too hooked up onto trying to achieve 100% occupancy. As we said yesterday, somewhere in the high 60s or so, at that point you're probably safe. Right? Because, yeah, as long as you have a few instructions that could execute concurrently from the same warp, you have enough work to keep the device busy. Yes? It can happen. It can happen. Again, in situations like where you have some complex calculation at the beginning. Right? Imagine you have something that involves divisions. Divisions are relatively expensive. The compiler, or at that point, the register allocator will say, hey, I'm probably safer by not redoing this division later on. I'm probably more efficient by not doing it later on again. So I want to keep it in registers. But then, yeah, maybe you're increasing the register pressure because now you're blocking this one register for keeping this data around. And so there's a huge range of heuristics where the compiler then just has to make these trade-offs between saying, hey, is it now more beneficial to recalculate this division, or am I better off by going out and pushing some of the variables into local memory? Those are heuristics, and the goal is to make it work in as many cases as possible, but
My question was, is there any fundamental reason why this cannot be improved by better compilers?
oh, sure. Well, and I mean, there is situations where you simply cannot, where at a particular time in your kernel, you just need to keep track of so much state that it uses more than whatever. As long as it's more than 32 registers, fine. You're just decreasing the occupancy. That might not be so bad. Once you're going beyond 256 registers per thread, our architecture simply cannot handle it. We don't have more than 8 bits to label registers. So at that point, it has to spill out into global memory or into local memory. So, but yeah, I agree. I mean, many of these things can be tried to be resolved by improving the optimizer of the compiler. And that's, as I said, that's an ongoing effort. But in some cases, it's simply impossible just because you have too much state that is being carried around. OK, did this thing about the occupancy kind of clear up a little bit, I hope? And here. Right, and I mean, this graph here also shows you that if your bandwidth limited, you might not need to get full occupancy to still achieve all the bandwidth that is available due to the hardware. If each one of your threads loads sufficient amounts of data, in this case, 16 bytes per thread, even at half the occupancy, at 50% occupancy, you're still getting the full bandwidth of the system. So you're still using as much as possible due to the hardware. Right? That's another thing. It's why do you want to get up there? Well, this bandwidth would be available due to the hardware, so you better use it, especially when your performance is limited due to the amount of data that you're loading and writing back. OK, so we had this one. All right, so far we talked about making sure that we have sufficient loads in flight and what the effect of those is. Now we're coming to the memory coalescence. That's something that we also touched upon yesterday. But yeah, the concept is, again, that you're issuing these load operations per warp. And so it's not absolutely necessary that all threads within a warp access exactly adjacent bytes. Right? First off, because the fundamental transaction happens in chunks of 32 bytes. So that's 1 byte per thread and not 1 float per thread. And B, because the hardware detects, it tries to minimize the number of requests that have to go out to memory to fetch this data that you're requesting. And I'm coming to a few pictures. Right? So when you're looking at the efficiency of how efficiently you load the data, There's basically two ways of looking at it. One is you're just counting the number of bytes that the application needs, and you're measuring the time that this chunk takes. And this gives you the bandwidth, right? So and so many bytes divided by the time that it took. That's the application's perspective. But then there's the other way of looking at it, which is, from a hardware point of view, how many bytes need to go across the wire between memory and the streaming multiprocessors. And those are the bytes that, all these extraneous bytes that you didn't actually ask for, but just get delivered because we're loading this stuff in chunks of 32 bytes at a time. There is something I haven't mentioned yesterday, which is broadcasting. So if all the threads in a warp access the same word, actually the same byte, at that point we have special hardware as well that only ships this one byte across the wire and broadcasts it to all the threads. Okay, so here we have different scenarios. This is like the best case where we have each thread in a warp accesses a float, right? So this means we need 128 bytes. They have to go across the bus. And yeah, I mentioned that the actual access happens in chunks of 32 bytes. So these are called segments. So we are loading 4 segments, and we're using all of this data that we ask for. So this is a perfect situation. Our bus, so the wires between global memory and the streaming multiprocessors, is utilized to 100%. Perfect. This is what you want to get to. Now, this is a different situation where you have a permuted access. So thread number 1 is accessing element 15, and thread number 2 is accessing element. Again, doesn't matter. The hardware resolves that. It looks at all the threads within a warp and figures out like what is the minimal set of data, the minimum number of segments that we need to move across the wire. So don't worry about accesses where individual threads permute the access, as long as they stick within a contiguous chunk of memory. This is a case which in many situations is not quite avoidable. For instance, again, a finite difference scheme where you just go through your data and you need to load eventually the value that you are responsible for plus the value 1 next to you. Well, the last thread in the warp, or in this case, let's say the one element left to you, the first thread will need to access an element that's sitting in a segment next on the left-hand side. So instead of the 4 segments that you would need, we need to load yet another segment. So instead of 4 segments, we get 5 segments that go across the wire. So that means instead of the 128 bytes, we're loading 160 bytes, which drops us in the utilization or in the effective bandwidth that we're observing to 80%, right? Which is just the extra, well, it's 5 over 4. Well, 4 over 5. Not tremendously bad. There's no way to avoid it. And that's actually something that, again, if you watched GPUs for a certain period of time, that used to be much worse in previous architectures. In previous architectures, you actually had the full 128 bytes that all the transactions were operated on. So in those cases, if you had a misaligned access, you would load, instead of 128 bytes, 256 bytes. So your bus utilization would drop down to 50%. So this is already quite a nice improvement. Again, geared towards the programmability, the ease of programming. Here is a case where we have a broadcast situation. But yeah, I actually misspoke before. Even in the broadcast situation, you actually a full segment at least. So a full segment meaning you're getting 32 bytes. And even though you're all the threads in the warp, all 32 threads, only want to get 4 bytes, you're loading the 32. So you're only using 1/8 of the data that goes across the wires. So these are just different scenarios that kind of give you a feeling of what to look out for. I mean, in many cases, it's just unavoidable. But it helps you to understand when the profiler reports you that you only have, whatever, a bus utilization of 12%, well, there's nothing you can do. This is just the hardware, plus, so the way that the hardware works, it delivers all this data, even though you're only asking for 1 word. And this is kind of, those are the worst cases where your accesses are scattered across multiple segments. Especially when you're just using, from each one of the segments, you're just using a single word. You're loading all this extra data, right? Even though you're just asking for 4 bytes over here, you're getting 32 bytes. And so the bus utilization actually can go down quite a bit. Yes?
Now, how come these lines you mentioned before, which are 128 bytes,
Right.
How come they?
Well, at this level, they don't. So again, remember, we do have a cache hierarchy. We have an L2 and an L1 cache. And the granularity, the cache lines of the L1 cache are actually 128 bytes. So they are 4 segments long. However, in Kepler, the ones you have installed on the on 30, in Kepler, the L1 cache is configured in a way that the global memory loads are not going through that cache. So in that case, the actual width, the 128 element width, is completely irrelevant. Even though we do have these cache lines, it doesn't matter. It's one of those situations, again, where from architecture to architecture, we shifted around with the different implementations or the different ways of how the memory system works. And so in some cases, it's still, especially when you compare with older generations, it's still worthwhile to think in terms of the full 128 line size. So that's why we kind of have a mixture between those, depending on which graph, which slides we're using. Okay, so that's the worst case. Let's look into an example. So here we have Saxby, so AX plus Y. So in a pure CPU implementation, you have a scalar times X element goes into Y, well, increments Y. Now, if you would do that on a CPU, and you would write it in a multi-threaded way, you probably would have thread 0 work on a contiguous chunk of memory because you're loading some data into your L1 cache and you're operating out of the L1 cache for this core on that part of the vector. And the next thread will have a disjoint part of the vector. So that's good in case of OpenMP or P threads. Now, what you see here is that depending on the number of elements that we work on per thread, we load data here with this base offset, which is whatever, the starting point for thread 2, plus 0 to the number of elements that we're working on. In pictures, if you're now looking at all the 32 threads at the same time, this means that thread 0 loads an element here, and thread 1 an element over here. So for our architecture, this would be horrible, right? If you think about the pattern we had before, because even though we're just requesting a single float from over here, we're going to get a whole chunk of 32 bytes around it. And the same over on this one. So the better way of accessing data for Saxby is that you have adjacent threads, feeding adjacent memory locations. This is the optimal case. So all that means is that instead of having a loop count, let's see, having a number of elements per thread that you're working on, and you're incrementing those, you basically increment by your block size. So the loop count here for 0, and then you're going up to this loop count 1, and all the threads within this thread block access the elements in the next region, in this next block. This is probably one of the most fundamental concepts in optimization, is you want to make sure that you have memory coalescence. Yes? It's basically one warp, yes. It is because all the memory accesses happen at the level of individual warps. But, right, so yes, here the width could be a single warp. Now the problem is you want to have more than a single warp per thread block because of the occupancy, right? Otherwise you have only 16, if we come back to this chart. Right, with a single warp per thread block, you're limiting yourself to 16 warps in total, because you only can keep track of 16 thread blocks. One warp makes 16 warps. So that's only a quarter of the available warp slots that would be filled. And so chances are, again, pretty high that you're ending up in a situation where there is simply no work to be done until everything else has been, all the other dependencies have been resolved. So you probably just, you don't want to have access just at the individual warp level. Also, the thing is that in CUDA, there is not really a mechanism of addressing a single warp. Right? We don't have a warp IDE. You can compute it. As I said, it's deterministic how the threads are counted, and so the first 32 threads will be in the first warp. But it takes additional calculation for doing that in the current form. And so there's not really an inherent benefit of doing that, of keeping here this chunk size here, the width of a warp. But you're totally right. The fundamental granularity is at the warp level. Yes. Okay. Now, this is all good and fine when you're talking about the simple cases, where each thread accesses an individual element of an array. But what happens if you have something like a 3D struct? Most typically like XYZ positions. Oops. Right. So you will, at one point, you will load data at your index into your temporary variable. Now, here's a picture. Oh, let's say it first in words. Basically, this loading of data into temp will be translated into a load of x, a load of y, and a load of z. And what that means is that thread 0 is going to load x first, and then in the next load instruction, you will load the adjacent elements, and finally the last ones. Horrible access pattern. Okay. So what you rather want to have, so it doesn't really matter. It simply says here in lots of words, you're loading all these gaps in between as well. So instead, what you want to do, and unfortunately I don't have a picture, would be that you're saying, I'm just loading a big chunk into shared memory, and I know that thread 1, the second thread, will now load an element that he's not responsible for. Right? The thread 1 will not work on the first position, but he's just loading it. We're loading it into shared memory, and then afterwards, once we've done that, we can start picking the individual elements out of it. So that's the problem, or the idea that on GPUs, it's actually better to have your data structures arranged as a structure of arrays rather than as an array of structures. Okay, so what we've described here, sorry for jumping around, but what we have here is an array of structures. And this is oftentimes a suboptimal pattern for accessing. It's just, yeah, in those situations, you probably want to load data from global memory into shared memory first, massage it there, and work out of shared memory, and then write it back out to global memory. The better configuration is where you have, so that's structure of array versus array of structures. So array of structures, usually not good. Structure of arrays, good. Right, so your access pattern should more look like point of x sub I rather than point sub I dot x. And there's a few other cases, right, where you want to have, for a strided access, you still want to be very close by rather than, so you want to have stride 1 rather than having a huge gap in between. And then completely random accesses, we saw that pattern just leads to loading, moving a lot of data across the wire that you don't really need. So these are just, again, that's not hard science. It's just good things to keep in mind when you're designing an application for GPUs, for CUDA. You want to have access patterns that are nice. So the ones like here. This is just a summary slide, what we talked about, right? We want to have aligned accesses. You want to have contiguous contiguous accesses of your data, and you definitely don't want to have scattering via strides or, yeah, usually via strides. The profiler can tell you a lot about that. So using the analysis button on the profiler, it will tell you that you have the strided memory accesses, for instance, and that you will not have, it will give you the effective memory bandwidth that you've achieved. And so based on that, you can kind of figure out what would be, what the core reason is for that poor performance. And I mentioned that yesterday, but in some cases, it's just not possible to avoid a scattered access, right? Your application might just need completely random elements out of a big matrix. In those cases, you may want to consider loading your data through the texture cache rather than through the through regular loads, because there we have, yeah, the texture cache is optimized for that type of accesses. But again, that's a finite resource. It's a finite cache size, so you don't want to use it for all your loads. I mean, you could say, do all your loads through the texture cache. Again, at one point, if you might just saturate that cache, and you're not ending up in having any benefit anymore. Was there anything else? Wanted to say something else and I forgot. Anyway. Oh, yeah, so here we have the the two slides on the caches. Let's go through those before break. But as I mentioned, there are caches in between global memory and the streaming multiprocessors. But keep in mind that you have this kind of random order in which the threads are being executed, and you have a huge number of those. Designing an algorithm for cache locality usually doesn't make sense. I mean, we basically say just ignore the fact that there are caches. Don't try to do cache blocking and load things and keep it in those L1 or L2 caches and assume that this is better than going all the way out to global memory. it's usually not the case, simply because you don't know at what point a thread will actually execute, and at one point it will get access to the data. It depends on so many additional facts, right? At the relative timing at what the warps are being executed. So designing an algorithm for L1 or L2 caches is not really a good software design. However, we do have this texture cache that can help if you have uncoalesced reads. The texture cache is only is for read-only data. In those cases, it might make sense to actually go through that path. And there's two ways of using it. One is to let the compiler handle it by declaring a variable as an array as const restrict. With the so that's in C, right? With restrict, you're saying that this pointer is guaranteed not to be aliased with another pointer. So the compiler knows for sure that this is the only way how you're accessing the data that's behind this pointer. And with const, you're saying that nobody else is modifying it. This tells the compiler, it gives it sufficient guarantees that this is indeed read-only data, and it can use this path through the read-only data, the texture cache. The compiler has to be conservative, and it has to be prepared otherwise that, well, even though you're saying that this is a const pointer, there might be another pointer that's referring to that address. And so what seems to be const is, in fact, not const. Somebody might be changing it under your foot. And therefore, the compiler cannot assume that this is a true read-only data. So just declaring a pointer as const is not sufficient information for the compiler to be sure that this is indeed just read-only data. Alternatively, in addition to using const restrict, there's a primitive. So basically a function that just is underscore LDG. And you're providing it an address, the pointer to this variable that you want to load, and it inserts this load instruction that gets your data through the texture cache. With const restrict, there's still a lot of ways to confuse the compiler, and so that it has to assume that still somehow it may not be possible to load this data through the read-only cache, and so it will fall back into the more safe regular data access path. So those are actually situations where it makes sense to look at the generated SAS code, right? Because when you use a construct like this, and you get the feeling that your code probably is not using the texture cache, that would be a situation. You're looking at the SAS code. Do I see the LDGs in my generated code? And then you know, well, at least it's there. In other situations, you may see that even though you declare the pointer as const restrict, the compiler decided not to use the load through the texture cache. And I know there's quite a few people in here who have never done CUDA before, and so this might seem like a lot of low-level tweaking, and it is. So don't get confused by this one too much. It's not something you want to address at the very beginning. It's something where, again, you will see when you actually go home now and you're working on a piece of code and you're running in the profiler, you're getting quite quickly into the situation where you're looking at it and you see, okay, I'm using 35% of my achievable bandwidth. So what? Yes, I know I want to get higher in my bandwidth, but what can I do? And yeah, so the first thing is you want to flatten out your memory accesses. You really want to make sure that you have coalesced accesses. You want to go ahead and make sure that you have your occupancy, keep it as high up as possible. And then if you're still not seeing any improvement, well, that would be another tool that you could have, another hammer to throw at this problem. Yeah, let's see what happens if I go through the texture cache. Again, this is not particularly well in alignment with our messaging, because it has this sense of trial and error attached to it. But at one point, just optimization drops down to something that's pretty much trial and error. The goal is to make the space of choices that you have to explore with trial and error as small as possible. Using profilers, using insight into the architecture, you can limit that to a very small number of different combinations of different experiments that you need to do. But in many cases, you will still end up with, having to do the actual experiment and see what it pays off or not. I'm probably getting fired for this, but oh, and here is again the messaging about L1 and L2 caches. Just don't ignore them. Okay, and we have a few more slides on const restrict. How this looks like down here. Let's go here just to illustrate it. Again, this would be for instance for the Saxby kernel, right, where the input data is now explicitly decorated as a restrict and as a const pointer. This will tell the compiler that yes, indeed, instead of loading this through the regular data path, you can use the texture cache. Or then alternatively, you're using the LDG instruction. Right? In some cases, it's not possible. It's not possible to declare a pointer as const restrict because, for whatever reasons, you have a predefined API that doesn't allow you to change the function signature, or you have whatnot, some other reasons why you don't want to change a pointer to const restrict. Maybe you need to change it later on or whatnot. But you have additional knowledge about your kernel that you know you need to load it in this form.
Why did you use the one step back output? What is with the restricting output?
It's not strictly necessary, but it's one of the things where telling the compiler that pointers are not aliasing, even if you're completely ignoring GPUs, that's in general a good idea, right? Because it gives the compiler more information. So even on the CPU, by declaring a pointer as restrict, you're actually helping the compiler quite a bit, and you allow it to generate better code. Right? I mean, it's all a hack around the fact that C pointers are so minimalistic and don't give you sufficient information about access patterns. This would never happen in Fortran. Are there any Fortran programmers here? Cool. Yeah, so that's yeah. Let's skip the discussions about the textures and stop here for a break. Okay.